Well, hello and welcome to everybody. Thank you so much for joining us today. Today is our fourth and final webinar in our series of online training webinars that we've been running for the last 6 weeks or so. So for those of you that don't know me, my name is Emily Giles, and I'm the lead specialist on the Science, Knowledge, and Innovation team here at WWF-Canada. And I live just outside of Ontario in what is the traditional territory of the Algonquin and Anishinaabe people. So today we've got a really exciting webinar for you. I think this might be the most exciting one out of the 4-part series. Today we're going to be looking at drones and ROVs for environmental monitoring. And we have some special guests joining us today from Korotu to help share more about some work that they're doing using drones and ROVs. So just for folks who maybe haven't joined some of these before, did want to let you know that we are recording these webinars and we're going to share them afterwards with you. You'll receive them over an email afterwards. And they'll also be available on the WWF Learning Library, which is a resource that we have sharing all of the tools and resources that we've developed to date at WWF to help let folks know about how to measure and monitor carbon in your area. And I believe Claire has just shared the link there for our learning library in the chat. If you have any questions as we go through the webinar today, please feel free to use the Q&A function. If you look along the bottom of your screen there, you should have a Q&A button. Feel free to type a question in there and we'll do our best to answer it as the webinar goes on. If we don't get to it while we're speaking, we'll hold on to it. And at the end, we will have a dedicated Q&A session where we'll read through those questions and answer them live. If you have any technical issues at all, please do email us at science@wwfcanada.org and we'll try and help you as best we can. So in terms of what we'll cover today, we'll do a quick round of introductions and then we'll just do a quick overview of what we've covered previously in the last workshop. Then we're going to get into some drone basics and talk about the different types of drones that are available for work in forestry. And then we'll get into how to actually plan a drone forest carbon flight. And then from there, how to actually do the analysis using that forest drone imagery. And then we're going to have a bit of a deep dive into a case study. Chelsea Bowler from our team in Newfoundland is going to share about some work that she's been doing with the Miawpukek First Nation using ROVs. And then finally at the end, we will again have that Q&A session. So the objective today, this is what we're hoping that you'll get out of the session today. We want you to be able to learn how drones and ROVs can be used for environmental monitoring. You'll learn about the different types of drone licenses that you need, go over kind of a drone basics or a drone 101. We'll talk about the types of drones that are needed for forestry, and then we'll get into actually how you plan a drone forest carbon flight, and then how to analyze that, analyze what you get from the imagery from that forest drone flight. And then again, we'll chat a little bit about ROVs and how ROV surveys can be done in carbon-rich habitats. Before we get into everything, we just want to do a quick round of introductions. So for folks who are joining us for the webinar, we'd love to hear from you, hear your name, your affiliation and role, and whereabouts you're located, either your location or community that you're from. If you don't mind just entering that into the chat, that will help us just to learn a little bit about who is participating today. And I'll turn it over to Cal on our team to kick off introductions.
Great, thank you, Emily. Hi, everyone. My name is Cal, but I go by Cal. I'm an associate specialist on the Science, Knowledge, and Innovation team at WWF Canada. My work stems from my experience working on ecosystem carbon cycling throughout Canada, particularly focusing on providing tools and information to build capacity of individuals who are also interested in this kind of work. So yeah, I'm excited to be here today to discuss drones and ROVs. And with that being said, I'll pass it on to Claire.
Hi everyone, I'm Claire Wark and I'm a specialist on WWF Canada's Science, Knowledge and Innovation team alongside Emily and Cal. I'm based in Collingwood, Ontario along Georgian Bay's south shore on land that's been traditionally managed by the collective Saugeen Ojibwe Nation. I spend my time at WWF Canada connecting with communities, leading carbon training and fieldwork initiatives, and supporting our carbon community of practice calls. So I'll hand it off to Chelsea.
Thank you, Claire. Hi, everybody. My name is Chelsea Bowler, and I am a senior specialist with WWF Canada on the Resilient Habitats team. I'm based on the west coast of Newfoundland in the unceded territory of the Mi'kmaq, specifically here, Korotu First Nation. And I work very closely with Miawpukek First Nation, who are based on the south coast of the island portion of Newfoundland and Labrador. And so I will get into a little bit more of my role and the work that we've been supporting the Guardian team with on the south coast as we get to the later part of today's presentation. And I think that's everyone from our WWF team, and I will pass it off to the Korotu team for their introductions.
Hi, everyone. Thanks for joining us. I'm Derek Robinson. I'm the Chief Science Officer at Korotu. I'm also an Associate Professor at the University of Waterloo. If there's anything that you think can be done with a drone, I've probably been involved with it, from small micro drones that I'll talk about today to really large 8-footers. And I look forward to talking with you guys on chat and presenting some of our work to you. I'll pass it over to Sean Rudd.
Thanks, Derek. Delighted to be here. Sean Rudd, founder and CEO of Korotu Technology. We're a social enterprise that builds software to enable communities to measure, monitor, and ultimately fund nature-based climate solutions. Today, I guess I'm wearing my advanced pilot's hat, and I'm going to be talking through the process of planning a carbon flight over a forest. I'll hand over to Manveer.
Hi, everybody. My name is Manveer. I'm a software engineer and product lead at Korotu Technology. I'll be mainly going over different ways you can analyze drone imagery that you get from the drone flights through software and get some useful statistics out of those. I'm based over in Vancouver, specifically on the coast, unceded territory of the Coast Salish people, the Kwantlen and the Semiahmoo specifically, I think. I think that's it for our team, so I'll hand it off.
Great, thank you. So Cal, we'll pass it to you to get started.
Thanks, Emily. So before we dive into the worlds of drones and ROVs, I wanted to give a brief overview of our previous workshop where we talked about measuring carbon in trees and vegetation. So in this webinar, we looked at how to conduct tree and vegetation surveys in the field using various tools, such as a laser rangefinder, DBH tapes and quadrats, and we use these tools to estimate the carbon stock through biomass estimations. Specifically, we covered how different plot sizes could be used to sample different heights of different classes of vegetation by height. So these include small vegetation plots for plants under 0.5 meters, medium vegetation plots for plants between 0.5 and 2 meters, and large vegetation for plants over 2 meters in height. As well, we introduced what we called an integrated plot design, and this is shown on the bottom right here, where vegetation from multiple plots can be sampled at the same time, and then the carbon stock values from each of the plots can be integrated together. In terms of measuring carbon stock, we showed how to set up a survey design and take measurements of vegetation to estimate biomass. For trees, this included measuring the DBH of the tree and the height of the tree. For shrubs, this was volumetric measurements as well as diameter at crown height. And for smaller plants that don't necessarily have those equations that you can use from survey data, we showed the clip and weigh method as a way to remove plants from the plot, bring them to a lab, and estimate biomass via those methods. And then given these bioestimates, we use the carbon conversion factor of 0.5 to convert these biomass estimates into an estimate for carbon. Lastly, we introduced a set of tools for setting up a sampling design and for automatically calculating the carbon stock from these measurements. And for those who are interested in this webinar, maybe you missed it, maybe you want to go back to it. It's available on our carbon measurement learning library. And there's a bunch of other resources on that page for those who are interested in field-based methods for estimating carbon. That's just a quick recap of workshop 3. And go to the next slide, please, Emily. So now, in this webinar, we're going to shift from taking measurements on the ground to the sky, discussing how drones can be used for environmental monitoring and carbon stock assessments. So I want to spend about 10 minutes just at a higher overview, going over the drone basics before I pass it off to the more technical teams at Korotu and Chelsea. And I do this because I recognize, people on this call can be coming from different backgrounds and experiences. So I want to provide a brief introduction to make sure we're all on the same page with regards to the terms used in the drone and ROV world, and as well as just to ensure we're communicating as effectively as possible during this webinar. So to begin, what are drones? Well, it's just a common name for a flying robot, and these can be robots that are fixed wings, that propel themselves like a plane. They could also have rotating propellers like a helicopter, but in either case, in a drone, the pilot of the aircraft is not on board the aircraft itself. And recognizing that a drone flight requires multiple components, not just, the drone, the UAV itself, but it actually requires multiple components. Transport Canada and the Canadian aviation regulations adopted the term remotely piloted aircraft system. And this is the official term to describe drones. And but however, given this official name, you'll also hear the more common names such as drones, UAVs, or UAS, unmanned aircraft system. So the definition of drones as systems is because, they cannot be legally flown by themselves. They require a pilot, a ground control workstation or a computer, and a way to communicate between the workstation and the drone. So this could either be via satellite, radio, or internet connection. And of course, the drone itself. In modern drones, the workstation and the communication link are integrated into the drone and the remote controller. So it looks a little simpler. And that's shown on the right there. That's a DJI Mini. So you can just see it's a drone and a remote, and that is the full remotely piloted aircraft system. Next slide, please, Emily. So how can drones be used for environmental monitoring? At a high level, you can attach sensors to a drone. You can fly over an area, and those sensors can collect data. The most common and basic form is just attaching a camera to a drone, and most drones even have cameras already attached to them. And this is great because you can take photos and you can take videos. So below here you have a photo of this estuary on the left taken from the ground, and then that same river channel taken at around 100 feet above the ground using a drone camera. So it's just nice to get that different perspective. And you can take videos, you can take photos, but there are many benefits to using drones. This includes the ability to access an area from the sky, reducing any potential disturbance to an area. This also means you can cover a large area in a relatively short amount of time, scanning the ecosystem with, as I mentioned, photos or videos. And another thing worth mentioning is that the drone world and the hardware and the software is a constantly evolving area of technology where the high cost of these high performing drones is decreasing, and the capabilities of the drones and the software to manage the drone data is growing as well. So yeah, that's one important thing to mention. Next slide, please. So some of the applications from collecting this drone data via aerial view. A couple of examples are taking videos or photos for wildlife monitoring. The images on the top right here are from a bird survey, where you can see on the small left photo, this was a drone photo taken from around 100 feet above the estuary, and we were able to zoom in and take that photo on the right, and we were able to capture each individual bird in that frame, and we were able to manually count each of the different birds. So this was an example of a manual wildlife monitoring survey. However, there are also software tools available that can automatically count very large populations. If you're doing caribou herds or big herds of animals, there's software that can identify them as well. So in addition to wildlife monitoring, drones can be useful for detecting and monitoring large ecosystem size events. This includes wildfires, impacts from storms or other disturbances. And this is especially crucial directly following the event, where the safety of entering the ecosystem on foot could be compromised. And doing an aerial survey is a good initial step just to ensure the safety of the people on the ground, and as well as obtaining information from the aerial view as well. And then lastly, this leads us into landscape scale and habitat mapping on the next slide. So through collecting drone imagery, it's possible to collect data over a large area and combine all that information together to produce a very high resolution map. So by processing and combining images together, this is called stitching. However, simply putting images together won't produce a very accurate map. These photos need to be corrected to match the geography of the location. And this process is called orthorectifying an image, and it produces what are called orthophotos. Lastly, you can combine orthophotos together to produce a spatially accurate map, and these are called orthomosaics. So on the right here, you can see that there are drone images. There's around 45 drone images on the left there, and then these were ortho-rectified to produce orthophotos and then stitched together to produce the orthomosaic, which could be added to a mapping software where they can be analyzed or added to a larger data set. And this is just a very high level idea of how habitats and ecosystems can be mapped with imagery. And the Korotu team will get into a little more details and a little more practical sense of how these can be analyzed. Next slide, please, Emily. So just having briefly touched on the introduction to drones and some of the applications for environmental monitoring, I also want to briefly touch on some specific barriers and restrictions that might be encountered when you first start working with drones. So the first is recognizing that there's a learning curve, and it's quite steep for drones. There are skills and knowledge needed to operate a drone. This includes maneuvering the drone safely and effectively in different conditions. Weather can play a critical role in safely operating a drone, and common conditions such as rain and winds can actually restrict the ability to fly. Additionally, there are hardware and software limitations. Different drones and sensors accomplish different tasks, and they usually have to be paired with specific hardware to analyze the data. And recognizing that these potential costs of getting the right hardware and the right software can add up quite a bit. And then probably some of the larger restrictions on drones are just the legal processes that regulate and restrict drone activities. So in Canada, when you're operating a drone, for example, you have to maintain what's called the visual line of sight, or VLOS. And this means you cannot fly your drone without being able to see your drone. So it's just one of the many, many rules for operating a drone in Canada. And on the next slide, to build on this, as part of these regulations, there are differences in drones licenses. So these range from having no license at all, where you're permitted to fly a drone under 250 grams, and many drones are actually built to be under this limit for that specific purpose. And then you can get the next level up, which is your basic license, which allows you to fly larger drones. However, there's still restrictions being related to where you can fly, specifically around people and in controlled airspace. And then the next level up is your advanced license, which gives you the ability to at least ask for permission to fly in most areas with larger drones in Canada. Next slide, please. So as a part of obtaining your drone license, there are certain knowledge requirements needed to pass the exam. And aside from these licensing aspects, it's just important when you're operating a drone to understand the basics of drone flight mechanics, as well as the legal structure surrounding drones and being familiar with some of the lingo that we've kind of been introduced a little bit here. So just to give an example, here is the drone basic movements. So these are your roll, which is the left and right movement along the longitudinal axis of the drone. Then you also have the yaw, which is rotating on the vertical axis. I like to think of this as the drone spinning. And then you have the pitch, which is the movement of the nose up and down, almost like a seesaw motion. So that's just an example of the knowledge, a little introduction to the knowledge needed to get into the licensing and to operating a drone. Next slide, please. Great. So when it comes to flying your drone, remember it is a remotely piloted aircraft system where you, the pilot, control the drone through a workstation and a communication link. So for most modern drones, this occurs through the remote controller interface. This could also be on an app on a phone or on a tablet as well. So the display shown here on the right is from a DJI drone, but most interfaces have a very similar interface as well as the same components. These include information on the drone state. So this could be battery life, the number of satellite connections, the remote battery life, as well as information on the drone sensors here. So you'll have the speed, the altitude, distance to nearby objects, and as well as automative tasks that you can perform. One of the most common automated tasks is return to home function, where the home is just a location and the drone will automatically fly back to that location. So just, before you get a drone up in the air, it's important to familiarize yourself with the interface, as it's a way for you to communicate and control the drone in flight. And next slide, please, Emily. And just on top of licensing, there are also physical equipment requirements to fly a drone, especially to do it safely. So of course, you need a drone to fly a drone, but you also need that remote control, that interface via smartphone. It's important to have, an appropriate takeoff spot like landing pads. You need storage if you're taking photos or videos. This includes, storage on the drone itself, as well as hard drives or a cloud subscription to keep a large database of these files. You also need some software requirements. And I know the Korotu team will introduce a little bit of software there. And the last thing I wanted to communicate is just to make sure that your drone that you want to purchase is compatible with both the software you're planning to use and that these drone and software capabilities will accomplish the specific goals you wish to achieve. So that's just, not every drone is compatible with every software. So you just want to double check everything to make sure you're buying the right drone. Now, with that brief introduction, I want to pass it on to the Korotu team who are going to go into a little bit more details. So I'll pass it on to you guys. Thank you.
Super. Thanks, Cal. And again, on behalf of WWF and Korotu, I want to thank everybody for joining us today. If you could move on to the next slide, please. I'm going to reinforce some of the materials that Cal just presented and talk to you for maybe 4 or 5 minutes about some of the drone classifications and its application in forestry. Next slide, please. We're going to start off by talking about the classification, and that comes to us from Transport Canada that's based on the risk and safety to society. So the class of drones that are easiest to get started with, pose the lowest risk, and are most safe are micro drones. These do not require any formal certification to fly. These are less than 250 grams, so they're quite light, but you are beholden to privacy and nuisance laws, and you have to refrain from flying around airports and in restricted airspace. Now, despite this flexibility, they have some limitations, and that's that the battery life is typically limited to 18 minutes or less. They're very lightweight, so they can be very susceptible to environmental conditions like wind, and their small size limits the distance which you can fly over a forest because, as Cal mentioned, you have to maintain visual line of sight. You have to be able to see your drone. So when it's small, it's harder to see it at farther distances. The next class of RPAS is known as the small RPAS, and these are between 250 grams and 25 grams, and they're much larger, and therefore they have greater constraints. Because of their size and their ability to cause damage or injury, you're required to obtain a basic flight license for operating in uncontrolled airspace. This is airspace where there isn't a lot of flight activity, or if you want to fly in controlled airspace where there's a high amount of air traffic, then you have to obtain an advanced flight certificate. You also have to maintain an altitude that is less than 120 or 400 feet. And this makes sure that there's an airspace separation between you as the drone pilot and people that are flying in aircraft. The benefit of the larger aircraft is that it can maintain flight for much longer periods and it can carry much heavier payloads. And because of their size, you can maintain that visual line of sight over a forest or conservation area for much farther distances. We've done this for up to almost 1 kilometer in distance. A final point to make here is that many of the limitations on flight activities can be overcome with approval from Transport Canada with what's known as a Special Flight Operations Certificate. Now, if we move to the next slide, then we'll move from aircraft to the sensors they carry, and we find that a variety of different sensors used in forestry and conservation practices, and they each collect different types of information. The first group of sensors I'll mention are passive sensors. As shown on the left of our little figure here, these are the sensors that passively take in light that is coming from the sun and reflecting off the objects that we're interested in, which in this case are trees, when the shutter on the camera is open. These sensors are typically relatively light RGB cameras that combine a portion of the visible spectrum, which is shown in the upper right, into one layer of information. So the same way that we view the world and we take that all in as one piece of information, the camera that is an RGB camera does the same. If we start to separate that information out into individual bands of information or layers of information that are like red, green, and blue, and some of the near infrared, then we're using what's known as a multispectral camera. The second group of sensors are active sensors, and they send information down to the earth and measure its return, as shown by the other drone with the black and red arrows. The most common sensor in forestry is LiDAR, which sends pulses of light down toward the forest and measures the length of time for that light to return to the sensor and the intensity of that return. Those pulses of light are hitting leaves and tree trunks, branches, and the ground, and return with the coordinate locations of those hits, which enable us to measure the structure of the trees and the forest. Some examples of these data are shown on the next slide, please. On the left is an optical RGB image from which we can use to identify snags, which you can see as the white leafless trees, coniferous trees in the upper portion of the image, and deciduous trees down near the bottom of the image. In the center of this slide are three bands of electromagnetic spectrum, or three bands of light. The top is our near infrared information. The middle is the upper part of the red portion of the electromagnetic spectrum, and the bottom is a fuller representation of the red portion of the spectrum. While it's difficult in the presentation to see the differences amongst these data, other than perhaps a stream in the upper left, when we start to combine these different types of information in different ways, we can actually produce the common index, which is the normalized difference in vegetation index, and other indices that give us insight into the tree and forest health. On the right, the image demonstrates the results from some of our LiDAR data acquisition on a field sample plot that we conducted. And with these data, you can see that they clearly articulate the height of the trees, we can count the trees, and we can get an idea of the structure. And with sufficient point density, we can even measure the diameter at breast height. Next slide, please. Now, there are many types of drones, many different brands of drones, but what you'll probably most often see are the ones from DJI. And why is that the case? Because they're incredibly user-friendly and they work really well. So in the upper left is the micro drone that we often use at Korotu, the DJI Mini 3. That'll cost you around $500 to $700. The other two images are of the DJI Mavic 3 in the upper right with a multispectral camera. That'll run you around $6,000. And at the bottom is the Matrice 300 with an L1 LiDAR sensor, and that'll run you around $20,000. I want to move to the next slide and note before we move on that with the optical data, which you can see on the left, we process those data using something known as structure from motion. We're generating structure, in this case, a three-dimensional point cloud or model of the forest from motion, which is the drone moving around the forest, taking pictures from different perspectives. The outcome is this point cloud data, which is very similar to the LiDAR data, which you see on the right, which is also a 3D point cloud. But these data from the LiDAR sensor are able to penetrate through the forest canopy that also enable us to get information about the topography, the ground surface. Both of these types of point clouds are used in the same way by Korotu to generate much of the tree count, biomass, and carbon estimates from our flight plans that Sean's going to show you next, and the estimates about those forest characteristics that Manveer will demonstrate afterwards. I'll be online here to answer questions as well as we move forward, so please feel free to do that in the Q&A. I'll pass it over to Sean now.
Thanks, Derek. And so Sean Rudd, founder and CEO, of course, and what I'll now do in the next few slides, if we just move to the next slide, please, is talk through the process of actually planning carbon flight. Now, Cal introduced earlier some of the different tools and technologies that you'll need in terms of drones and software. If you're going to run a structured flight over a forest to be able to collect data such as biomass or carbon, you are going to need a little bit of extra software in terms of some flight planning tools, because you're going to want to run a very structured mission. So lots of tools available. Today, I'm going to be using some largely free tools, Ancient Land, Flyleechy, and Google Earth Pro, all available free or at low costs. There's plenty of commercial options out there, and Korotu develops our own tools as well, Land Steward. So you've got lots of choices, but you're going to want to use something. So if we just move to the next slide, please. As we go about planning these flights, quite a lot of detail to work through. I mean, the very first one, of course, is area and purpose. Where do you want to fly and why? In this case, I'm going to be flying Samuel Smith Park in Etobicoke to the west of Toronto. And excuse me, sneeze there. The area, it's shown in the middle of this map. It's a couple of hectares of forest with some grassland around it. And I'm going to want to be doing that repeated times, because I'm going to want to go back a number of times and monitor carbon growth and potentially loss over time. So with that in mind, it's quite a small area, but it's an area that the public can come into. I might get some dog walkers or families coming in there. Students from the nearby college. So I have got some considerations in terms of flow of people coming through. And for that, and then the flight area itself it's near to Pearson and City airports, but it is outside of the main control zone for both of those. So as I factor those different things together, I'm going to go with a micro drone, a small, less than 249 gram drone that has less regulatory compliance issues and is less of an issue for flying over people. And it's low cost. I can fly it lots of times. But of course, it is susceptible to wind and weather, and I do need to make sure that I'm not going to be a nuisance. So just some considerations, which leads me to choose the RGB drone and structured for motion. So next slide, please. So given the drone that I've chosen in my area, I'm going to want to start planning the flight in some detail, and I'm using Ancient Land for this, which is freely available software. So I'm going to draw a polygon around my area. It's going to be slightly larger than the forest that I want to scan, ideally at least 30 meters each side. You get a little bit of blurring effect on the edges. So we don't want that. We want to get some clear area. Plus, it's great to have a bit of clear land to put ground control points in that I'll come to. The way that I'm going to fly it is a grid, otherwise known as a lawnmower pattern. I fly there and I come back forward and backwards. And I'm going to want to have lots of overlap. Because I'm flying structure from motion using an RGB camera, I want the pictures to overlap. And I like to fly 80-80 overlap, 80% at the front, 80% at the sides as a minimum, which is why you can see all those dense points. And then height is going to be important. Cal talked about the ability to cover very large areas, which is obviously great. But you do lose some fidelity, some detail. I'm going to be flying at about between 40 and 60 meters for this flight. So some considerations about the level of height to get good accuracy. So next slide, please. And some other things to think about. I don't want my images to be blurred or particularly shadowed. So ideally, I would have cloud-free images and no wind. And I'll be flying low and slow, so that'll improve the quality of the images that comes through. In terms of orientation of the sensor, the camera, I'm going to point it straight down. There are cases where we might use something else, but straight down tends to be the best for forestry. NADA is the technical term, and I'm going to want to be able to link this back to the ground. So in the images here, you see that little black and white tiled area. That's a ground control point. And I'm going to be putting at least 5 of those around the forest area. That'll make it much easier to orientate the images that I gather back to the Earth's surface later on, and it'll improve the quality of the output. So with those considerations, I'm going to go ahead and actually plan the flight in some stages. So using Ancient Land, I would select the area, and next slide, please. Zoom in, and you can see that that's the area. And next slide, please. Just zooming a little closer and switching to satellite. That's the forest area we looked at in the middle. And next slide. I'm going to draw an area around that with a polygon. Next slide, please. Change the amount of overlap, high level of overlap, 80-80 overlap, and also adjust the height to, in this case, 43 meters for a ground sampling distance of 1.5 centimeters. Gives me a nice crisp image of those trees, not individual leaves, but certainly enough to see the crown structure, which I'm going to need for the carbon mapping that Manveer will explain. On the next slide, you see I've just orientated that flight to come back towards me each time. That's not absolutely critical, but I've placed the pilot, that's the little dot, on the eastern side in the middle there. You might be able to see. That's where I'm going to fly from. I'll probably put some observers around as well to deal with members of the public and also keep an eye on the drone. But I know this area, I can see it. And having the drone come back each time is really helpful if I have to do things like battery changes. The drone comes back, bring it down, do a battery change, and resume the flight. It tends to be most efficient. So once I'm comfortable with all of those points, I've got the flight planned. Move to the next slide. I'm going to export that and bring that into, in this case, Flyleechy. And each of those points that I was pausing at, the little waypoints, will be an area that a photo is taken out. I'm going to make final adjustments. And on the next slide, I just check that everything is set correctly. There's quite a few settings here. I won't drain them, but one that I will mention down the bottom is use online elevation. So I'm going to want the drone to stay a consistent height above the land. Now, for those that have visited this park, you'll know it's pretty flat, so it's not a big issue. But if your forested area is very hilly or even mountainous, keeping the images at a consistent height above ground will make it much easier to stitch them together. If you get a more than double distance in height, like 40 and 80 meters, the ability to stitch the images together decreases a lot. So once I've got all the settings set, I'm just going to check the flight in 3D, and I'm using Google Earth Pro here. And just what I'm doing is I'm just doing the last check of the flight before I export it. If you go to the next slide, I'm checking that I've got good clearance above all of the trees. I obviously need to be above those, but also any buildings around, any other concerns. It's a chance to check that my flight is looking the way that I was planning it to. And I always like to do this in the office before I go in on site to the location. So once that's all good, I'm just going to now export load it into my software that I'll actually use to execute the flight. In this case, we're using the Litchi app, which is available for a small fee. And you can see that it's loaded up on an iPhone or an Android device. And if I'd connected my drone, I don't know if the drone will show here, but yeah, I've got it's not showing very well, but I've got a DJI Mini 3 in my hand. If I connected, I could even simulate the flight. So with that, I've got everything that I need to go ahead and run the flight. And after I've completed the actual exercise in the field, got full batteries and safety checks, I'm going to take the data from that, upload it, and Manveer will explain the process of processing that to get some carbon data. Thank you.
Maybe a mic check there, Manveer.
Oh, sorry. My bad. Right. So like Sean said, my name is Manveer, and I'll be taking you through the process of analyzing drone images and getting some useful metrics for them. So next slide, I'll just be going over an overview of the types of metrics you can expect. So there are a lot of different types of software, and from most of them, you can expect to get, if you input RGB images from a normal camera, you can expect to get 3D data such as a canopy height model, an orthomosaic, or 3D point clouds. From those, you can analyze those the same way you would analyze LiDAR data. You can get biomass estimations for the plot. You can detect individual trees and get interesting statistics on the trees that you detect, such as the biomass for the trees, as well as the heights and diameters. And there are a lot more statistics that we'll be showing you. So next slide, I'll just be going into a piece of software developed by Korotu called Land Steward. We use it to analyze plots. And so this is a project that the project that Sean flew, Samuel Smith, Urban Park in Toronto. So you can see a 3D visualization that was generated from images taken from a drone flight. And you can view this from different angles. Next slide. To help you get a better sense of the plot. Next slide. You can zoom in and out to see individual trees. And once you've zoomed in and seen a particular tree you want to look at, you can click the button at the top that says show tree points, and next slide. It'll show you the tree points in the plot. You can click on any one of those. You can see one towards the center there I clicked on. It has a height of about 16 meters and a diameter of almost 20 centimeters. This estimates for biomass as well as the actual position of the tree. So maybe after you've done analysis on this, you can go into the field and actually hand measure the tree and compare the accuracies. Next slide. You can zoom out and get a full visualization of the entire field. And you can also visualize this in another way, which is if you click the color scheme at the top, you can, next slide, view this in a computer-generated color scheme where the ground points are brown, the tree points are green, with the higher points being shown as a lighter green. You can export this view if you click Export to Orthophoto, next slide, and get an image that's easily shareable between you and your colleagues in case you want to share the plot data. Next slide. Leaving the visualization, you can see a summary of the plot and all the statistics in it. For example, this plot was about 2.8 hectares, and it had about 120 trees per hectare. You can see information on the trees, such as the average diameter, height, and the tallest tree in this case was about 22 meters. There's also estimates for biomass on the right, where the biomass is also separated out into different metrics, such as the upper canopy biomass, the soil biomass, the below ground biomass, etc. There's also other options on the left that you can see, such as viewing the biomass. Instead of biomass, it would be the carbon mass or the CO2 mass, but I won't go through all those in depth. Next slide, you can also view a list of the individual trees and get the dimensions and the general statistics on them, such as the height, diameter, and biomass. Keep in mind, these are all estimated. So yeah, this was a short summary of the different types of metrics you can expect to get from using some drone analysis software. We've used a lot of different software in our experiences, and so if you had any questions about using our software, LandSteward, or any questions in general about the process of analyzing drone imagery, feel free to get in contact with us either by sending this message here or sending us an email anytime you need it. So, yep, thanks. That was all for me. I'll hand it off to Chelsea, I think, for her next part.
Thank you so much, everyone from the Korotu team. Hello, everybody. Again, my name is Chelsea Bowler, and I'm going to speak to you a little bit about a case study here in Newfoundland with Miawpukek First Nation. So as I mentioned briefly earlier, Miawpukek First Nation is based on the south coast of Newfoundland. So you can see that in the map image on the left-hand side there. And this is the wonderful Guardian team that I was working with a few years ago. So WWF has been partnered with MFN for probably the last 4 years, going on about 5 years now. And our very first project with the Guardian team was a browned monitoring blue carbon. So blue carbon being carbon that's found in the marine environment. And they were particularly interested in eelgrass habitat. And so that's really where we were focusing most of our monitoring efforts and training efforts. So we did do the drone monitoring for this region, also used in the blue carbon space. And we partnered with Hakai Institute, who's actually based out of British Columbia. And we worked with a gentleman by the name of Chip Mountain, and he's the lead guardian with Miawpukek First Nation, based in BC. And so we did some great virtual training with him. And then he actually came down to the nation here in Newfoundland to provide some hands-on training in that first summer with the entire Guardian team. You can flip to the next slide there, Emily. And the issue that we had with the drones is that apparently the water in Newfoundland is quite different than the water in British Columbia. So these are just a few little snippets from the drone imagery from Newfoundland, but as you can see, it's extremely difficult to tell what's under the water in these particular photos. So depending on the currents and the wind and the sun and cloud covered and all these things, even though the Miawpukek First Nation uses drones to look at the nature and extent and density of the eelgrass beds in their nations, this was actually not a tool that we could use in Newfoundland. So it was really great in the sense that all of the Guardians did get higher training for drones, and they're actually using these drones now on more terrestrial-based applications, but we still had the issue of not being able to fully monitor the eelgrass beds in this particular region. Next slide, please, Emily. So we looked at remote operated vehicles, or ROVs. And so what is an ROV? It means just that we are operating this machine. They go underwater, similar to drones. They're sometimes referred to as underwater drones. The qualifications necessary to operate these are a little bit different in terms of what is required for the aerial drones. So you actually don't need a license to operate these smaller units that you can use off of the side of a dock or off of the side of a vessel. There are much larger ROVs that are sometimes part of vessel equipment on big research vessels, etc. Those are not the type of ROVs that we'll be covering here today. So I'm just going to talk a little bit about the particular model of ROV that we've been using with Miawpukek First Nation and also with some of our other projects. So we have been working pretty closely with Deep Trekker, who's a Canadian manufacturer of ROVs, and they have many different models of ROVs. And so I've used some of their smaller models for different types of work, but the most recent Revolution is the name of the model. We've been using that with Miawpukek First Nation around eelgrass and other seabed type of monitoring. So I'll just get Emily to play the video. It's just about a minute, just over a minute, I think, and it'll just give you a sense of the type of machine that this is and how it operates underwater. You can flick to the next slide, Emily, please, and thank you. So yeah, that was just a little snapshot, I guess, of the particular model that we are using. And so when you're choosing the type of drone that you want, or not drone, sorry, but ROV, underwater drone that you want to use for the type of habitat monitoring you're doing, there's a few things that you want to consider. So the reason that we actually went with this larger drone compared to some of the smaller models is that it has additional thrusters. So we were working in areas with higher currents. And you also want to take a peek at what's the actual type of monitoring you want to do. So you can take still shot photos, you can do the videos. There's other sensors you can attach to it to look at depth and dissolved oxygen and turbidity and a bunch of other things. So there's a bunch of different attachments as well. You can get water sampling attachments, you can get ground grabber attachments. So there's a lot of different things that you might want to consider, especially if you're using this type of device for more than one type of sampling. So the reason we're using it here is in the Miawpukek territories, there has been a lot of environmental changes over time to the marine ecosystem, mostly due to the influx of fresh water from the hydro plant that's been installed and operating since the 60s. And more recently, they're looking at expanding this hydro work. And so previous knowledge in the region is really based in traditional and local knowledge. And so the community knows that there's been extreme changes over time, but using these types of tools can help us look at more of the quantitative changes over time, looking at the actual carbon values from the cores we're taking, but then really looking at the extent and density of the different beds around the territory. Yes, and as I already mentioned, they can be, ROVs can be used in areas where drones aren't suitable, like on the south coast of Newfoundland, the drones did not work for us in terms of the blue carbon piece. And we are pairing it with other environmental monitoring as well. So a little bit more details on what we're actually doing besides looking at the temperature and depth and salinity and these more kind of environmental factors. We're also pairing this with environmental DNA monitoring. And so what this does is we actually just take a water sample. We use a different device for the water sampling, kind of alongside the ROVs. And then we send this sample to the lab and they run through and they're able to tell us actually which species are found in the area. We're focusing specifically on species at risk in this region and looking at culturally significant species. And so we're looking closely at 3 different species of wolffish, American eel, Atlantic salmon, and Atlantic cod as well. And so it's just, I just wanted to share a little bit more about that because it is beyond this carbon project. Even though the project started as a carbon project about 4.5 years ago, we've now been building on that just to get a better sense of what species are actually utilizing that habitat outside of its value for carbon. And so that's been really important to the community, and it's been able to support them in making informed decisions when it comes to consultation committees where they're engaging with different industry like hydro coming into the region, and just a better way at directing their natural resources department and how they want to steward their lands and waters. Next slide, please. So a little bit about the equipment needed. This will vary a little bit depending on the type of ROV that you'd like to use for your project. So there are kind of 2 options, at least for the model that we're using. So we have battery and direct power. So we actually have it set up for both. So you can use the batteries and we can also plug it into the generator. So that is an extra piece of equipment you would need if you decide to go the direct power route, having a generator aboard the vessel, or if you're down by the docks and doing something that's closer to land, just having that available to plug in. The setup comes with its own controller, so you don't use your phone. It just has its own kind of, it literally just looks like a video game controller with a screen on it, like you saw in the earlier video. And any of those additional sampling and mapping tools that I briefly mentioned earlier, you would just speak to the manufacturer about exactly what you would need to best suit your project. I found them very helpful at weeding out the software, but also the mechanical pieces that were not necessary for a project at all and ones that we might want to consider. So one of the packages that we included in our particular setup was the nav package. And so this is really helpful when underwater might be a little more blurry or you're setting up those surveys. I don't have screenshots of those actual surveys because this coming summer is actually the first time that we're going to be running those surveys, but it is very similar to the drone surveys that Korotu had presented for those aerial drones. And so before you actually leave, if you're going on the vessel or if you have internet access on your vessel or to the location you're doing your sampling, you can actually preset these waypoints in a very similar way that you do with drones, having that overlap area. And then you can set, you know, we believe that the eelgrass bed is here and it just does these survey points. So you're operating it from the vessel or operating it from the dock, but it's just kind of doing its thing. And so you can get it set up with different types of tethers, different lengths of tethers. We have ours set to 300 meters is kind of the deepest area that we're going. So we have a 400-meter tether on it. The device itself is rated for 400 meters. And we're going to be looking at least 7 different eelgrass beds this upcoming summer, where we've already taken some of those core samples for the carbon. An option for this setup too is having a monitor, like a separate monitor. So you do have that real-time screen for the operator of the ROV. However, if you have kind of like a bigger crew or you have a few folks in the cabin of the boat, you can actually have just like a computer monitor that plugs into the controller with an HDMI cord, and you can see that real-time video in kind of a larger space. That's a nice option to have as well. Next slide, please, Emily. So this is just a little bit more about that nav package, and it's really essential for the survey components of what we're doing. And so this is another really short, about 1-minute video that just talks a little bit more about that nav package and some of those survey, or they call it mission mode, that you can use with this particular ROV.
It's a different world underwater. Most technology we take for granted on land simply does not work. Navigating in this environment can be quite the challenge. At Deep Trekker, we see this as an opportunity. Because GPS doesn't work underwater, we're faced with some big questions. How do you know where you are? Where are you going? And how do you make it simple? The answer: meet the Deep Trekker Revolution Nav Package. First, to fuse underwater location and positioning together in a way that makes inspections and surveys simple for anyone. Seamlessly combining GPS navigational sensors into the Deep Trekker Bridge software, operators have the comfort of having all the display on one simple-to-use control system. Operating in strong currents? No problem. With the nav package, the Revolution ROV is equipped with autonomous station holding sensors for even greater stability control. Post-dive, take your recorded GPX data to visualize the entire mission. Share waypoints and points of interest alongside your recorded videos and images with your team or customer, easily and succinctly. Join the Revolution Nav ROV and have your underwater operations become more intelligent, autonomous, and simple. To learn more, visit deeptrekker.com.
Thanks, Emily. You can go to the next slide now. So just to talk a little bit more about this knowledge and data display. So as you can see, we're taking lots of underwater photos and videos, and that's one of the main portions of what we are doing with Miawpukek First Nation, in addition to those actually more quantitative surveys. And so another piece of what the nation is wanting to do is just tell a story about this region. And so some of those images can help, even just from a more storytelling perspective, in addition to that more quantitative piece. So what we have kind of started, I just have a screenshot here because this story map isn't actually live or public quite yet. So we're still in the process of developing it with the nation and our other partners. But this putting this together kind of happened back when we were doing primarily the blue carbon work, and we've been growing it as we've been doing more environmental monitoring with the eelgrass beds and involving species at risk as well. So what we have here is, as I mentioned, there's a lot of traditional and local knowledge about the ecosystem in this region. And so we have kind of this braiding or weaving of different knowledge systems where folks will be able to, once we go live with this, come to this page and see some of that quantitative work that the Guardians are doing, in addition to some of the storytelling from the elders and other community members sharing about the changes in the region over time, why certain habitats or culturally significant species matter to the community. And then we're interlayering that with some of the Western science mapping and just more science around the blue carbon piece. You can just click for the extra photo to pop up there, Emily. Perfect. And so this is just a screenshot of later on in the story map. So you can actually see that we have like some GPS points there. So these are the points in the nation where we're actually taking those core samples for the eelgrass. And this summer, the Guardians will be going back to these regions with the ROV to get a better idea rather of the extent and the density of those eelgrass beds. So we do have some of those locations identified, but once we develop this work a little bit further, we'll have full polygons. that actually show how far out and how deep the eelgrass beds go. And then we'll be able to have the information around the actual carbon cores, so having the carbon values, the stock values, but also the accumulation rates over time for many of the sites that we got good readings off of. So all of this information is currently being compiled in addition to that traditional knowledge that we will be sharing through this space with the nation. Next slide, please. So I just wanted to talk a little bit about some suggestions for best outcomes. And as you can tell, this is new for this nation as well, in addition to myself using these different tools for this more quantitative monitoring. So what I really enjoyed about the group that we are working with Deep Tracker is they offered a lot of training. And so we were fortunate enough last year to actually travel to Ontario, where their headquarters are based. And you kind of saw in that last video, a gentleman kind of standing on a dock operating one of the ROVs. So that's actually one of their training facilities. So it's a man-made lake there, and they have a cabin there that you have all your gear set up at. You can do some troubleshooting, do some surveys, and kind of practice in that space. So we really enjoyed that. And then what we really enjoyed was being able to have them come out to the nation and do some additional training in the field. So although it was great to kind of go to that facility, we got to see the manufacturers, see the drones being built, and also be able to operate them in that space. There were quite a few differences operating out on a boat in the marine ecosystem versus in a man-made freshwater lake in Ontario. So it was really great to have some time between that initial training and the second training where the Guardians were out on the boats using the ROVs in certain locations, getting the hang of the mapping, etc. And then having specific questions or troubleshooting that we needed to go over, and we had Deep Tracker come out and do that in-person training. And we were able to kind of do that training joint with Miawpukek First Nation, in addition to Mamaka, which is another Indigenous branch of technicians doing work in the marine space. So it was really cool to have multiple groups do that training. And it's kind of created this little network of support as well in the region for folks that are using this type of technology for environmental monitoring. So although the manufacturer is always open for us going back to them with questions, there's also kind of this little network of Guardians that are doing work in the region, which is really great. Also really appreciate the free online trainings that are available. So a couple of those videos that you already saw, but on the Deep Tracker website, they also have like a knowledge center. So they have all of the different videos you could possibly need for troubleshooting, for just regular functions, getting used to the pieces of equipment that you have, all of the manuals, etc. And one thing I think I mentioned a little earlier in my presentation, but I'll just reiterate it again, is we are working ourselves, we work in a very remote area. So cell phone coverage, isn't constant throughout the entire region. And especially for some of these kind of further off sites that the Guardians will be monitoring. It's really, really helpful if you're able to have internet access. So if there's any way for that to be like hooked up on a boat, in our case is what we're working on. Like I said, you can pre-plan those surveys and you can have those kind of set GPS points for your missions. But if something happens where you plan to go to one site and the weather's too bad to go to that one, and you change it in the field, kind of what your plan is for the day or for that week, it's really a lot more user-friendly if you can kind of switch things around while you're on the boat and set some new waypoints. So that is something that I would definitely recommend. And then the other piece is just repetition, repetition, repetition. The more you do it, the more you play around with the machine, the more you're working in different environments, the easier and easier that operation will get. I personally found it quite challenging, but I've also had my teenage daughter out on the boat with us, and she is like a pro. So it seems like just like playing a video game if you're used to that. But the more you do it, the easier it will be to just get familiar with the device itself and also just how it operates in different environments. Next slide, please, Emily. So that is all I have to share specifically on our ROV. And I think I'm going to pass it back to Emily if there's any questions that have been unanswered. I'm sure she'll go through them and we can all help to answer those together.
Yeah, great. Thank you so much, Chelsea. And thank you again to the folks at Korotu and for everyone for their presentations today. I don't know a lot about drones and ROVs, so I found this very informative. So we now have some time to answer some questions. I noticed some questions have been coming in on chat, and our team here has helped to answer them as they've come through. I see one more has just come through, so I'm going to, oh, it's actually not a question, I think it's more of a comment. So just thanking Derek for the explanation. And Shantia says, it's very interesting how this technology may help to calculate carbon content of peatland. It'd be great to see the sensor technology development in the future to avoid overcalculation. Great, so thank you for that. And I noticed someone also put a question in the chat. Oh, thank you, Agatha, for answering that one. So Jane had asked if DJI is the software or a type of drone. So Agatha Rudd answered that for us, saying it's a drone, and provided the link there for it. Someone also had their hand up. I believe Matt had their hand up, so I did just want to pause and make sure. Matt, if you want to go off mute and ask a question, you're more than welcome to. Or maybe it was just an accident there that you had your hand up. Okay, accident, no problem. All right, thanks. If there's no other questions, let me just check and confirm. Okay, we're all done there. So just moving on, this was our last and final webinar in the carbon training series that we've done. So just another reminder that we will email the recording if folks are interested in getting the recording, and it will also be shared on our Learning Library website, where all of the recordings from all 4 of the webinars that we've done will be housed. We also do host a carbon community of practice here at WWF, and we invite anyone who's interested in learning more or sharing resources, sharing stories about the work that you're doing. Please reach out to us, and we'd love it if you could join our carbon community of practice. It's national in scope and includes practitioners from many different backgrounds. So we have a call scheduled for this April 23rd, where we will be focusing on wildlife and carbon specifically. Sorry, wildfire. I always say wildlife. Wildfire and carbon specifically. So please reach out to us if you're interested in joining that. We also do have a team that is very much interested in helping to support your in-field work or providing training if that's of interest to you. So please don't hesitate to reach out to our team if that's of interest to you. And I'll just make sure that you've got all of our contact information here. So if you want to reach anyone here at the WWF team, you can feel free to reach out to us at science@wwfcanada.org. And we've got Korotu Technology's email address here for you as well if you'd like to reach out about anything that you learned today. So thank you so much to everyone for joining today. And yeah, hopefully we'll be able to gather and share some more information together sometime soon. Thank you very much. Enjoy the rest of your day.